Hello friends, this is fourth session on numerical analysis of BSc 5th semester. In this lecture, I would like to explain you about the valid significant figures. So let us have a recap of the previous session. In the previous session, we have discussed a couple of examples on errors, absolute errors, relative errors and percentage errors. And at the end of this session, we will be able to understand the concept of valid significant digits, and we will be able to solve a couple of examples which involve the concept of valid significant digits. Now, let us have a definition of valid significant digits. Before going to define the valid significant digit, I would like to recall one important thing which we have seen in our primary school. For example, if we have a number 2354, here this is the units place, this is tens place, this is hundreds place, and this is the thousands place. So therefore, when we write this number 2354 in the expanded form, it would look like 2 into 1000, 2 into 1000 because its place is thousands place, 2 into 1000 plus 3 into 100 plus 5 into 10 plus 4 into 1, that is the units place. So this is the way how we were expanding the given number. In the similar way, if we have a number with a decimal place, the same procedure we used to follow. That is, this is 2 in the tens place, therefore 2 into 10, the 1 in the units place, therefore 1 into 1, plus 3 in 1/10s place. This is 0.1, 0.3 means 3 by 10. So 3 by 10 means 3 into 10 to the power of minus 1. This is 0.35 means 0.05. 5 is in 100th place, therefore it is 5 divided by 100, therefore it should be written as 5 into 10 to the power of minus 2. So therefore, when we expand this number, it looks like this. So by recalling this important concept, we can generalize the thing over here. A number x with the digits alpha 1, alpha 2, alpha 3, dot 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 alpha n. These are the digits which are constituting the given number x. It can be expressed in this format. Just as I have explained you, this is the general format. So alpha 1 is the first digit into 10 to the power m. M is the unit of the place in which alpha 1 appears. Just like 3 is the unit of the thousands place, that is, it is 2 into 10 to the power of 3. Just like that, alpha into 10 to the power of m. Like that this will be there, the expansion. This is the general form of the expansion. Now let us go for the literal definition of valid significant digits. So how to define the valid significant digit? Now, so the digit alpha n. See, valid significant digit means I have told you that x contains so many different digits. X is a number which is the combination of several digits like alpha 1, alpha 2, alpha 3, dot dot dot, alpha n, dot dot dot. So if alpha 1 is a valid significant digit, alpha 1 if it is valid significant digit in the given number x, the digit alpha n in the number x is said to be valid significant digit if the condition is here. You look at this condition. If the absolute error in x, we know that absolute error is absolute of x minus xa. This must be less than or equal to 1 by 2 into 10 to the power m minus 1. This is very important. So what is the meaning of this? That is, the absolute error in is less than or equal to half. 1 by 2 means half of the unit of the decimal place in which the number the digit alpha n appears. Alpha n is the digit which is present in the nth place. Alpha n is a digit present in the nth place of the given number x. So we have to write the unit of that particular digit and we have to multiply half to that, and we have to see this condition, that is absolute error must be less than or equal to half of the unit of decimal place in which alpha n appears. So that is the definition of valid significant digits. Further, there is an important note. So let us try to have this important note. So what is the note? We know that relative error is absolute error divided by the absolute value of x. This we know very well from our previous sessions. So therefore we can have a value of this from this particular step. We have seen in the previous step that absolute error is given by this particular thing. So in place of the numerator, which is nothing but the absolute error, in place of that we will write the value, that is it is less than or equal to, this is half of 10 to the power of m minus of bracket n minus 1 divided by absolute value of x, that is absolute value of x is, this is always less than or equal to first digit, alpha 1 is the first digit into its unit. That is, if we have the number 2947, this number is always less than or equal to 2 into 10 to the power absolute error in this absolute value of this number is less than or equal to 2 into 10 to the power 3. That is the that place value we have to consider 2 into 10 to the power of 3. Now if we have this thing, the expression looks like this, and if we simplify this, in the next step we are going to simplify this, and if we simplify this, it looks like so after simplification of this expression, we will have the RHS as 1 by 2 means 0.5, and this and these two together, when we simplify these, we will have 10 to the power of n minus 1 in the denominator. So it is 0.5 divided by alpha 1, that is the first digit into 10 to the power of n minus 1, and this is the relative error in the given number R if there are n valid significant digits. If there are n valid significant digits, then the relative error must be this much. We have seen that when there are n digits present in the given number, that is, if the nth digit is a valid significant digit, the absolute error is this much. And when the same thing, when there are n valid significant digits are present in the given number, then the relative error is given by this particular expression. So with the knowledge of this particular concept, let us move on to solve an example here. Now let us consider the first example, which is having the concept of valid significant digits. So here is a question. We have to find out the relative error in the number 13.74. This is the number given here. If all its digits are significant, how many digits are there? 1, 2, 3, 4. So all its digits are significant. Therefore here n value is 4. N value is 4. X is the given number and first digit is 1. Alpha 1 stands for the first digit, and in the given number the first digit is 1. All the digits are significant, means n is equal to 4, and x is the given number, that is 13.74. So this is the data we are having, and we have to find out the relative error. We know that the relative error is given by this expression. Just now I have explained you how we get this particular expression. So this is the standard formula we have obtained in the previous section, and now we are going to use it. So this is equal to numerator as it is, in the denominator alpha 1 is the value 1 here, into 10 to the power n value is available as 4 minus 1. So when we simplify this, so this is 0.5 into, this is in the denominator 10 to the power 3. So it is 0.5 into 10 to the power of minus 3 if we write it in the numerator, or else 0.5 divided by 1000. So 0.5 divided by 1000 is nothing but 0.005, that is. So relative error is this much when the given number has all its digits as the valid digits. So this completes the solution of the first problem. Now let us go for the second one. Look at the second problem, it is quite important. Here we have to find out how many digits must be taken in the value of square root of 180. We have to find out how many digits are there which are valid in such a way that the error is not exceeding 0.1%. This is very important at this moment to understand here that when the error is given as percent, you should understand that it is the percentage error given. So therefore, we are taking over here the percentage error. So error is not exceeding 0.1. Therefore, percentage error is less than or equal to 0.1. That is the data we have to collect here. And what is the other data given? X value is the square root of 180. That is, x value is here square root of 180, which when computed using our scientific calculator, it is 13.4164 ... It is an irrational number. It will have infinitely many non-recurring decimal places. So therefore, this is the number x in fact, and we have to find out how many decimal digits may be taken into account in such a way that its percentage error is less than 0.1. That means here we want to truncate the decimal places. We want to consider only few decimal places of this number in such a way that the percentage error is less than 0.1. Now let us start the work. So what is there? The definition of percentage error we are using here. Percentage error means relative error into 100. On LHS we have kept this thing, and on RHS 0.1 as it is. So we have done nothing to the right hand side, we kept it as it is. So LHS is relative error into 100, RHS as it is. So in the next step you take this quantity to the other side. When you take 100 to the other side, it comes to the denominator. So relative error becomes 0.1 divided by 100. Now we know the definition of relative error in this particular situation. That is, when we want nth digit to be valid, its relative error must be 0.5 divided by alpha 1 into 10 to the power of n minus 1. And if we simplify this in this particular case, because A1 that is alpha 1, the first digit here is 1. The first digit is 1, therefore it is 1 coming over here. 0.5 divided by 1 into 10 to the power of n minus 1, or it is simply 0.5 divided by 10 to the power of minus 1, only this quantity. Now this is the value of relative error as far as the n digits are valid in the given number. We want to find out what is n. So now we shall substitute this value in the left hand side of this equation. We have seen this equation as equation number 1, that is relative error is less than or equal to 0.1 divided by 100. On LHS, we are going to substitute the value 0.5 divided by 10 to the power of n minus 1. This is less than or equal to on RHS 0.1 divided by 100 means 0.001. This we have simplified. Now let us take this denominator to the other side. It directly comes to the numerator. Left hand side is 0.5 less than or equal to symbol as it is, this quantity as it is here, and now this, when it comes to the other side, it comes to the numerator. Now let us simplify the things. When we simplify, simplification is quite interesting, you please look at that. Okay, now let us simplify the right hand side. How we are simplifying it, you please see. This is 0.5. 0.5 means 5 divided by 10. This all of us know. 0.5 means 5 divided by 10. And wait for a moment, please. You don't consider this particular thing. Directly, we are simplifying from this step to this step. So what we have done, 0.5 less than or equal to 0.5. This is this in the next step. I want to tell you that the 0.5 less than or equal to symbol we kept as it is. Now this 0.001, it has been taken to the left hand side, therefore it directly comes to the denominator, and this numerator has been written as 10 to the power of n into 10 to the power of minus 1. So this is the one intermediate step we have written over here. That implies 0.5 means 5 divided by 10. 0.5 means 5 divided by 10. This we know very well from our primary school knowledge. 0.5 means 5 divided by 10, and 0.001 means in the denominator, it is in place of point, we will write 1. In the denominator, we will write like this. Here, instead of 0.1, we write 1 and then 0, 0, 0. So it is actually 1 divided by 1000. So 1 divided by 1000 in the denominator becomes 1000 divided by 1 in the numerator. So this has been written like this. Now let us simplify this. And on RHS, it is about 10 divided by 10 to the power of minus 1 has been written as 1 divided by 10. So this is the simplification. And in the next step, yes, what happens to the left hand side, you please see. The left hand side will be simply 5 into 10 to the power of 3. This is less than or equal to, on RHS only 10 to the power of n remains, because 10 to the power of 1 which has been cancelled with 10 to the power of 1 which is there in the denominator of LHS, and it is 5 into 1000 in the left hand side, and on the right hand side it is 10 to the power of n. Now it is 5 into 10 to the power of 3, it is 10 to the power of n. Now by looking at this, we can very easily guess that what should be the value of n. What should be the value of n? This is very important. We have to find out the value of n. Now you please observe over here, if we take n is equal to 3, what happens? 5 into 10 to the power of 3 is less than or equal to 1 into 10 to the power of 3. This is not true, because 5 into 10 to the power of 3 is greater than 10 to the power of 3, 1 into 10 to the power of 3. Therefore n cannot be 3 or less than 3. So what can be n? N can be either 4 or greater than 4. So when we choose n as 4 or greater than 4, then this inequality will be valid. Therefore from this expression we can get the value of n as n greater than or equal to 4. So this is how we have solved the first example, and at the end we can say that there are at least 4 valid digits taken in the value of a square root of 180 so that the percentage error is 0.1. So this completes the solution of the problem. So I hope you understood very well how to use the concept of valid significant digits to solve the examples. Now let us move on to the multiple choice questions. These are the simple questions. You can answer them. Please try to answer these questions and write your answer in the comment box. And these are the questions. You please have a look at them. And you can solve more and more example on this topic by using the reference of this book. And with this, let me stop. Thank you.